Welcome to 5.2. Today we're going to start integrating over curvy regions, and I think you'll find that the real challenge in these problems is the setup. So let's start with just a setup problem. We want to find the area of this green shaded region by integrating the function 1 over the region and 1dA, where dA is either going to be dx dy or dy dx, and we're going to set up for both. So if we're integrating with respect to y first, then you want to think of the region as broken up with vertical lines. And the curve that the vertical lines start on is your lower limit. So the y limits are going to go from the function x cubed to those red dotted lines leave up here at the equation y equals 8. So 8 is our upper limit. And then for the x limits, you say, okay, for which x values do I have those vertical lines in the region? So that's going to be x going from 0 to 2, because this point right here is 2, 8. That's where those two curves intersect. So our double integral looks like this. It's going to be 1 dy dx, and y goes from x cubed to 8, and x goes from 0 to 2. Okay, if you integrate with respect to x first, you want to think of the region as being broken up with horizontal lines. And the curve on which the horizontal lines start is your lower limit for x. Now, they start on the y-axis, so this is the equation x equals 0. So our x limits are going to go from 0 to, they leave over here on this curve. Now we have to solve, instead of y equals x cubed, we solve for x equals y to the 1/3. So they leave at y to the 1/3. And then the y limits on this one are pretty easy. You can see y goes, it starts at 0 and it stops at 8. So this one's going to be 1, we're going to go dx first and then dy, and x goes from 0 to y to the 1/3, and y goes from 0 to 8. Now, I find some students who have trouble when I really tell them, use those lines, actually draw the lines in to determine your lower limit and your upper limit. They find that that's really helpful. So I strongly suggest you do that. Let's do another one. We're going to start by sketching and shading the region of integration. Now, here's the important thing. You can't sketch or graph an expression. You can graph an equation. So when I look at this, I say, okay, I'm starting with y. So my equations will be y equals, the lower limit is x squared. So y is going to start at x squared, and the upper limit's x, so y is going to leave at x. So I draw a picture, y equals x squared, y equals x, and those are my y limits. And then for how much of the region do I shade? Well, then I look at the x limits. X goes from 0 to 1. So it's starting here at 0, and it's going all the way to this intersection point, which is 1, 1. So we're getting the whole region. All right, and I want to label the boundaries with equations. So this is y equals x squared and y equals x. Okay, now we want to reverse the order of integration. I'm going to draw a new picture. I'm going to be integrating with respect to x first. So I need to solve both of those equations for x. X is y and x is root y. And I want to think horizontal lines. So my new integral for b, double integral, x is going to go from y, that's where it starts, go left to right, to root y. The integrand just sits there, xy squared, dx dy, and then y goes again from 0 to 1, because that's the value up on the y-axis where the region ends. Okay, so let's evaluate. So again, we pull out the inside integral and label it. So integral 1 is y to root y, xy squared dx. Okay, that's 1/2 x squared, y squared. Y squared is a constant. You're integrating with respect to x between y and root y. Now you're going to plug those limits into x. So I'm going to leave the 1/2 out. When I plug root y in for x, I get root y squared, which is just y, times y squared. So I get y cubed. And when I plug y in for x, I get y squared, which is y to the 4th. Okay, and now integral 2, we take the answer to integral 1, and we use the limits from the outside integral, 0 to 1, and that's a dy. Okay, that's, I'll leave the 1/2 out again, 1/4 y to the 4th minus 1/5 y to the 5th between 0 and 1, which is 1/2, a 4th minus a 5th. When I plug in 0, I just get 0. So that's 1/2 of, let's see, that would be 1 over 20. So I get 1 over 40. And that's my final answer. Okay, I want to show you how you can use Desmos to track down your mistakes if you were to make a mistake. So suppose you evaluate this, and on integral 2, you get 1 over 50. So one thing you could do to figure out whether you made a mistake on integral 1 or integral 2 is to go to Desmos and plug in integral 2. So the way you'll do that, on Desmos, the way you get an integral is you type int. And it'll give you a spot for the lower limit, the upper limit, and the integrand. And so I already did that for integral 2, and you can see I got 0.025, which is the same as 1 over 40. Now, there are two possibilities here. Either Desmos is going to get the same answer as you got for integral 2, or it's not. If it gives you the same answer that you got, if you get 1 over 50 for integral 2, then you know you evaluated integral 2 right, and you made a mistake with integral 1. So you need to go back and do integral 1 again. If Desmos tells you a different answer for integral 2, for example, integral 2 is 1 over 40, then you know you made a mistake evaluating integral 2, and you can go back and redo integral 2. And by the way, Desmos does do double integrals, you can see up here, but that won't tell you where you made your mistake. Okay, let's do another one. Again, we want to sketch the region of integration and then do the integral. So the region is bound by x equals 0, that's the y-axis, y equals x, that's this line here, and y equals 3, that's this line here, and y equals 1, that's this line here. So our region is this. Now I want to evaluate the double integral 2x ln y dA. So I get to choose whether I want to do dy dx or dx dy. Now you can see in my picture here, I don't want to go y first. If I go y first, I'm using vertical lines, and notice the lower boundary changes halfway through the region. So I would need 2 double integrals. So I'm going to erase that, and I'm going to go horizontal lines. If we go x first, then we can do it with 1 double integral. So this is x equal y, and this is x equals 0. So my double integral will be 2x ln y. I'm going to go dx dy. X is going to go from 0 to y, and then y, I have those horizontal lines starting at y equals 1 and ending at y equals 3. So those are my limits on y. Okay, so integral 1 is going to be the integral from 0 to y of 2x ln y dx. So we're integrating with respect to x. That's x squared ln y between 0 and y. I plug those into x. That gives me y squared ln y, and when I put 0 in, I just get 0. So that's my answer to integral 1. So integral 2 is going to go from 1 to 3, y squared ln y, and that's going to be dy. Okay, this is an integration by parts. So make a little box here. U will be ln y, du is 1 over y dy, dv is everything else. That's y squared plus the differential dy. And then v, remember we integrate here, 1/3 y cubed. All right, and so this is equal to, I'm going to give you an alternate notation method for an integration by parts with a definite integral. And I kind of like this one better, actually. So we're going to go uv minus the integral of v du. So that gives me 1/3 y cubed ln y minus the integral of v du will be 1/3 y squared dy. And then I'm going to put brackets on this whole thing and a 1 and a 3 outside. And that indicates I'm going to get my final answer and then plug in those limits. And so this is still in brackets, 1/3 y cubed ln y minus, that would be 1/9 y cubed between 1 and 3. Okay, when we plug in 3, we get, that would be 9 ln 3 minus 3 cubed over 9 is 3. And then when we plug in 1, ln of 1 is 0, so 0 minus 1/9. So that gives us 9 ln 3 minus 3 plus 1/9. Now, my open math will accept that, or you could go 9 ln 3 and combine fractions to get minus 26 over 9. Okay, and then one more, and I'm not going to actually do this because you have a video that explains how to do it. This is a homework problem, but I just want to mention a couple of things. What's going on here is you've got a surface up here, that's z, and you want to find the volume underneath that surface over a triangle in the xy plane. And so to set up the region of integration, you really don't need to know what z is. You're just going to go x and y. And then with these three vertices here, notice all of the z coordinates are 0. That's because you're lying in the xy plane. So you can just plot the xy coordinates of those three vertices, and there you've got your region of integration. And you could either go y first or x first. It really won't matter because both will just require one double integral. So your volume will be the double integral of z, 3 over 1 plus x squared. And you're either going to have, I'll put a dA, you're going to have dy dx or dx dy, depending on how you want to set it up. And that is the end of this section.